All right, hello everyone. So today we're working on a discrete math problem. We have solved the following congruence for x. So we have x is congruent to 3 mod 5, x is congruent to 5 mod 7, and x is congruent to 2 mod 9. All right, so notice first of all that the greatest common divisor of 5, 7, and 9 is equal to 1. So they're all, we say, pairwise, relatively prime to each other, okay? And because of that, because it's equal to 1, we can go ahead and apply the Chinese Remainder Theorem, okay? And yeah, if it's not equal to 1, then the Chinese Remainder Theorem would not work out necessarily, the solution. You have to go with another route. That's what we'll be concentrating on today, though, applying the Chinese Remainder Theorem. All right, so the Chinese Remainder Theorem basically says if you have a series of congruences, x is congruent to a1 mod m1, x equals a2 m2, etc. And all these numbers are relatively prime to each other. Sorry, the m1, the m2, all these integers are relatively prime. Then there exists a solution to that system of congruences, okay? So how do I find that solution? It's a matter of doing some steps. The first step is going to involve finding this number m, which is equal to multiplying the m's, the numbers that we're modding here, so 5, 7, and 9. So we're going to take 5, let me do this in red here, 5 times 7 times 9. So that is going to be 315. Now, one thing I suggest you do is to leave it in the factored form, and we will use that 315 later on as well, but 5, 7, and 9, and keep it that way, that's it's going to be beneficial. Here's why. So we form this object called m, and then we're going to find these objects called m1, m2, m sub n. Okay, capital M sub 1, capital M sub 2, etc., capital M sub n to be specific. So m is that 5, 7, 9, and I'm going to keep it in this factor form. I'm going to divide this by m1. m1 is just the first number we were looking at the congruence of, which was 5. So this would equal 63, because the 5's cancels, you only have 7 times 9 left. For m2, you have 5, 7 times 9 divided by 7, and that's equal to 45. And last but not least, you have m3, which is 5 times 7 times 9 all over 9, which is 35. All right, and then the next part 3, in my opinion, is the hardest. We're going to solve a system of congruences here. And that system, yeah, you have, in this case, I have 3 congruences that I wrote, but you can have much more than depending here. The way it works is that you're going to take each of the m1s and capital M1s and the lowercase m1s. You're going to make equations with them. So the equations look something like this. Capital M1 is 63. Y1 is congruent to 1 mod 5. Next is M2, which is 45. Y2 is congruent to 1 mod 7. And last but not least, 35, y3 is congruent to 1 mod 9. And what you're trying to do is you're trying to solve all these equations, okay? And there is a solution, because, you know, you look at the numbers such as 63 and 5, 45 and 7, 35 and 9. Those are all relatively prime numbers. And we have this rule that you have a solution to this types of congruent equations when you have, first of all, a 1 in these positions, and your numbers over here and here are relatively prime. So there are solutions. How do I find the solutions? A couple ways of doing that. One, you can use the Euclidean algorithm to do that and go backwards. It takes a little bit of time. Or the other thing you could do is you could go ahead and solve these by inspection. So for example, if I take 63, y1 equals 1 mod 5, if you, let's say, plug 1 in, you get 63 times 1. Is 63 times 1 equal to congruent to 1 mod 5? No, because if you subtract 1, you get 62. And 5 does not go into 62 evenly, so that doesn't work. So how about maybe 2? 63 times 2 is 126. Is 126 congruent to 1 minus 5? Yes, it is, because 126 minus 1 is 125. 5 goes into 125 25 times. So that's what I mean by inspection. You're just like, yeah, let's try some numbers out. Now, these numbers can be positive or negative as well. So y1 is 2. y2 is going to be a minus 2. And y3 is going to be, let's see here, 35 times 1, 35 times, actually negative 1 works, okay? 35 times negative 1 is negative 36, minus 1 is a negative 36. 9 goes into negative 36. So these are your 3 numbers right here. So we did it by inspection, and I would suggest you stop the video and try to do that yourself. But again, it was just a matter of plug and play. Sometimes that's really hard to do. It's not easy. Then I would go to the long division and work with that, with the Euclidean algorithm. Okay, so we got our numbers, and the next part is finding your solution, and it's equal to this expression right here. So x equals a1. So a1, a2, a sub n are all the numbers that I had here on top. Those are the 3, 5, and 2. So you're going to have 3 times m1, which was 63, times y1, which is 2, plus a2, which is 5, times m2, which is 45, times y2 is negative 2, plus last but not least, an, which was 2, times big M3, which is 35, and y3, which is negative 1, okay? And you would go ahead and multiply these out and see what your solution is. And your solution here, let's see, it would be negative 450 here, negative 70, and then 63 times 6 is 378. Yeah. So 378 minus 450 minus 70. Equals minus 142. But this number, as I wrote here, I wrote congruent sign, minus 142 mod 315. It's always mod what your big M was, capital M. And yeah, this is the correct number. You could also add 315 to this number, and that would also be a solution. That gives you 173. Okay, so any number congruent to 173 mod 315 would actually work. 173 would be essentially like our smallest positive number here that would work. But there's an infinite number of solutions. Anytime you add 315 to 173, that'll be a solution. Okay, and yeah, I wish I could go into more time of why the solution works out, but that would take some time, and it kind of defeats the purpose of showing how do you compute a solution using the Chinese Remainder Theorem. All right, well, thank you for your time.